Tonight, we're going to explore one of the most quietly profound contradictions in all of modern science. The sun, a furnace of burning plasma, pours its heat across 93 million miles of empty space. And yet that space, the vast ocean between the sun and the earth, sits only a few degrees above absolute zero, which is 459 degrees below zero on the Fahrenheit scale. A blazing star. A freezing void. Both true at the same time. The light itself crosses the gap without warming anything it passes through. The vacuum cannot hold heat, because there is almost nothing there to hold it, barely one atom in every cubic centimeter. Temperature, it turns out, is not a property of space. It is a property of matter. By the end of tonight, you're going to understand why the vacuum between stars is cold in a way nothing on Earth can ever be. How radiation carries energy across that emptiness without heating it. And what this single idea reveals about stellar furnaces, spacecraft thermal design, planetary habitability, and the slow, quiet fate of the universe itself. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Most people think they know what temperature is. They feel it every day. A warm afternoon, a cold glass of water, the heat radiating off a stove. Temperature feels like something an object possesses, the way it possesses color or weight. We talk about cold air and warm sunlight as though cold and warm are ingredients those things contain. But here is where the first surprise arrives. Temperature is not a substance. It is not a property the way color is a property. It does not live inside objects waiting to be felt. Temperature is motion. Specifically, it is a measure of how fast the atoms and molecules inside a material are moving and vibrating and colliding with each other. Think about a room full of people at a crowded dance floor. Everyone is moving. Some nights the music is slow and people sway gently, barely shifting from where they stand. Other nights, the beat is fast, and every person is spinning and bouncing and colliding with whoever is near them. The room has not changed. The number of people has not changed. But the energy in that room is completely different. That difference is what temperature measures, not a thing added to the room, a behavior of the things already in it. Hot means the atoms are moving fast, vibrating with high energy, colliding with tremendous force. Cold means they are moving slowly, nearly still, barely interacting. And then there is the logical end of that scale. If cold means slow, and slower means colder, then the coldest possible state is when all atomic motion stops entirely. Everything stilled. No vibration, no collision, nothing. That point has a name. Absolute zero. It falls at negative 459.67 degrees Fahrenheit, or negative 273.15 degrees Celsius. Below that, nothing can go. There is no colder. Motion itself has reached its floor. This is not a trivial detail. This is the entire foundation. Because if temperature is a property of matter, if it measures what atoms are doing, then the next question follows immediately. What happens when there is no matter? Space is not full. We picture it that way, in films and photographs, studded with stars and wrapped in color. But the space between those stars is very nearly nothing. Not thin air, not a weak atmosphere. The density of matter in interstellar space sits at roughly 1 atom per cubic centimeter. 1 atom. In a space the size of a sugar cube. Let that settle for a moment. Then consider what you are breathing right now. The air around you contains approximately 25 million trillion molecules per cubic centimeter. Written out, that is a 25 followed by 18 zeros. If the interstellar vacuum were a vast empty room and you were trying to find matter in it, you would be searching for a single grain of sand inside a room the size of a concert hall. 1 grain. In the entire hall. That is the density of interstellar space. Wait. This changes everything about the phrase we take for granted. When people say space is cold, they picture cold as something the vacuum holds, a frigid substance stretching between the stars. But temperature requires matter to move. If there is almost no matter, there is almost nothing to have a temperature. Not cold in the way ice is cold, not cold the way a winter night is cold. Space does not have a conventional temperature in any meaningful sense. It is not cold. It is empty. Not nearly empty. Not mostly empty. Functionally, profoundly empty. The statement we grew up with turns out to be imprecise. Space is cold is a shorthand that collapses something strange into something familiar. The familiar version feels true. The accurate version is stranger and harder to hold. And this is where the second half of the mystery opens. If space cannot hold heat, if it has almost nothing in it to be hot or cold, then what exactly happens between the sun and Earth? The sun is burning at millions of degrees at its core. Its surface blazes at nearly 10,000 degrees Fahrenheit. That energy is enormous. And yet it crosses 93 million miles of essentially nothing to reach the surface of our planet. Warming oceans and driving weather and sustaining life. That vacuum, the same vacuum that cannot hold a temperature, somehow carries heat across the width of the inner solar system. How does that work? The answer has nothing to do with atoms carrying energy from one place to another. It has nothing to do with matter at all. And understanding it will require rethinking what energy transfer even means. That question is what the rest of tonight is built around. So let's start there. Not with space, with heat itself. Heat moves. We know this instinctively. Touch a hot pan and you feel it. Stand near a fire and you feel it. But the mechanics underneath that feeling, the actual pathways energy takes as it moves from one place to another, are worth pausing on. Because there are exactly 3 of them. 3 ways heat can travel, and 2 of them will fail before they even begin when we bring them to the question we left open a moment ago. The first is conduction. When you touch a metal spoon that has been sitting in a hot pot, heat moves directly from the spoon into your hand. What is actually happening is this. The atoms inside the hot metal are vibrating rapidly. Your skin is in direct contact with those atoms. They collide with the atoms in your skin, transferring their motion. Your atoms speed up. You feel warmth. The more atoms collide, the faster the transfer. This is why a metal surface and a wooden surface sitting in the same room at the same temperature feel completely different to the touch. Metal feels colder. Not because it is colder, it is not colder. Metal conducts heat away from your skin faster, pulling energy out more quickly, which your nervous system reads as cold. The temperature is identical, the rate of conduction is not, but conduction has one absolute requirement: matter in contact. The atoms doing the work have to be physically adjacent to transfer motion. Remove that contact, and conduction stops entirely. Space removes that contact. In the near vacuum between planets, atoms are not adjacent. They are not even close to adjacent. As we covered earlier, interstellar space holds roughly 1 atom per cubic centimeter, about 1 atom in a space the size of a sugar cube. Those atoms are not meaningfully colliding. They are not transferring energy from one to the next in any useful sense. Conduction across the vacuum of space is effectively 0. The first mechanism fails. The second is convection. This one is easier to picture. Put a pot of water on a stove. The water near the bottom heats up, expands, becomes lighter, and rises. Cooler water sinks to replace it. This cycling motion, hot fluid rising, cool fluid descending, is convection. It is how warm air rises from a hot surface on a summer afternoon. It is how heat circulates through a room with a furnace running. But here is what convection actually requires. A fluid dense enough to form currents. You need mass in motion. Bulk material carrying heat with it as it moves. Space has no such material. There is no fluid between the Sun and Earth. There is no medium thick enough to form any kind of current. The same emptiness that eliminates conduction also eliminates convection. The second mechanism fails. 2 down, 1 left. Radiation is different, profoundly different. It does not require matter at all. Electromagnetic radiation, the class of energy that includes visible light, infrared heat, ultraviolet rays, X-rays, and more, travels as waves through a perfect vacuum at the speed of light, roughly 186,000 miles per second. It needs no atoms to push through, no medium to carry it. It moves through pure emptiness as easily as it moves through air, actually more easily, since air absorbs and scatters some of it. And this is the only mechanism left standing in space, the only one that works. The Sun produces radiation across a wide spectrum. Visible light, the range our eyes detect. Infrared radiation, which we feel as warmth on skin even when our eyes register nothing. Ultraviolet radiation, which carries enough energy to damage living tissue. The kind responsible for sunburn. X-rays, streaming from the corona, the outermost layer of the Sun's atmosphere. The output is enormous, spreading in every direction, into space, at the speed of light. That output crosses 93 million miles in about 8 minutes, and arrives at Earth. But here is where something important becomes visible. Something easy to miss if you're thinking about heat, the way we usually think about it. Radiation does not heat the space it crosses. It cannot. Think about a flashlight turned on in a completely dark room. The beam leaves the bulb and travels through the air toward the wall. But the air itself does not glow. You cannot see the beam from the side. You see only the lit circle where it strikes the wall. The light is moving through the air, but the air is not lighting up. Only the wall, the matter the beam encounters, becomes illuminated. Now, apply that logic to the vacuum of space. Radiation leaves the Sun. It travels for 8 minutes across 93 million miles. And during those 8 minutes, it passes through essentially nothing. There is almost no matter in that corridor, so there is almost nothing to absorb it. The energy is there, racing through the void, real and measurable, but it has nowhere to land. The vacuum itself does not warm up. This is the key principle. Radiation transfers energy only when it strikes matter. When electromagnetic waves encounter an object, those waves cause the object's atoms to vibrate faster. The object absorbs the energy and its temperature rises. Without matter to encounter, the energy simply continues moving. The moon shows this in sharp relief. The moon has no atmosphere, no layer of gas to distribute energy across its surface. One side faces the Sun, the other does not. The sunlit surface reaches around 260 degrees Fahrenheit. The shadowed surface drops to around negative 280 degrees Fahrenheit. That is a difference of more than 500 degrees between two surfaces separated by a few thousand miles, the width of a world. The only variable is whether radiation is arriving. Where it arrives, the surface absorbs energy and heats dramatically. Where it does not arrive, nothing heats anything, and the surface radiates its own energy away into space until it approaches the floor of what temperature can even mean. Not gradual, not partial, total. The same Sun, the same distance, the same space surrounding both surfaces. One receives radiation, one does not. That single difference produces a temperature gap that would be lethal in either direction. And this resolves the paradox we opened with. The Sun heats Earth. That is true. But the Sun does not heat the space between the Sun and Earth, because there is essentially nothing in that space to heat. The energy crosses the vacuum without warming it. It arrives at our atmosphere, our oceans, our continents, and the absorption begins. Atoms in our air and water and soil pick up that energy. They vibrate faster. And what we call the warmth of a sunny afternoon is the result. The vacuum is transparent to energy. It is not a barrier. It is not a medium. It is a passageway that radiation crosses without leaving a trace. But radiation doing the crossing is only the beginning. The more interesting question is what happens at the other end, when that energy finally arrives. How our atmosphere intercepts it. How some of it is trapped, and some reflected, and some absorbed at depth. That is where the story gets considerably more complicated. Radiation is not only something that arrives, it is also something that leaves. Every object that receives energy also emits it. This is not a quirk of certain materials or a property of hot things only. It is a universal rule. Any object with a temperature above absolute zero radiates energy outward in the form of electromagnetic waves. The physics behind this is called black body radiation, which simply means thermal radiation emitted by any object based on how hot it is. And the hotter the object, the more energy it radiates, and the shorter the wavelength of that radiation. The sun is extremely hot. Its surface reaches roughly 10,000 degrees Fahrenheit. At that temperature, it emits radiation that peaks in the visible range, the narrow band of wavelengths our eyes evolved to detect. That is partly why sunlight looks white. The sun's peak output lands exactly where human vision is most sensitive. Earth is much cooler. Its surface averages around 60 degrees Fahrenheit. At that temperature, Earth radiates too, but at much longer wavelengths. Wavelengths in the infrared range, invisible to the human eye, but detectable with the right instruments. You radiate too. Your body, at 98.6 degrees Fahrenheit, constantly emits infrared radiation outward in all directions. This is not a metaphor. It is why thermal imaging cameras can see people in total darkness. The cameras are not detecting reflected light. They are detecting the radiation you are already broadcasting. Point one at a wall, someone leaned against a minute ago, and you can still see the outline of their shape in the warmth they left behind. So every object is doing two things at once: absorbing incoming radiation, emitting outgoing radiation. The balance between those two determines whether an object heats up, cools down, or holds steady. Think about a bank account. Money comes in, money goes out. If deposits and withdrawals are equal, the balance holds. If withdrawals exceed deposits, the balance falls. Temperature in space works the same way. Energy arriving from an external source is the deposit. Energy radiated outward is the withdrawal. When they match, an object reaches what physicists call its equilibrium temperature, the point where incoming and outgoing energy balance and temperature stops changing. Distance from the sun largely governs this equilibrium for objects in our solar system. The farther from the sun, the fewer deposits arriving per second, and the lower the equilibrium temperature. Mercury is the nearest planet to the sun. Its sunlit side receives intense solar radiation, with almost nothing in between to weaken it, and almost no atmosphere to moderate the effect. The temperature on Mercury's sunlit surface reaches around 800 degrees Fahrenheit. That is hotter than a conventional oven running at full power. Mercury is simply in a position where the energy deposit is enormous, and the equilibrium settles at a punishing level. Neptune sits at the opposite end of the solar system, roughly 2.8 billion miles from the sun. At that distance, the sun's radiation has spread across an almost incomprehensibly larger sphere. Very little of it arrives at Neptune per square foot of surface. The average temperature on Neptune is around -370 degrees Fahrenheit, cold enough to freeze almost anything we can think of. The balance sheet makes sense. Very low deposits, very low equilibrium. But here is where it gets strange. Neptune's temperature, cold as it is, should actually be even colder. When scientists calculated how much solar radiation Neptune receives at 2.8 billion miles and worked out what the equilibrium temperature should be, the numbers pointed lower. What they measured instead was warmer than expected. Not slightly warmer, meaningfully warmer. Neptune radiates roughly 2.6 times more energy into space than it receives from the sun. That ratio does not make sense if the sun is Neptune's only energy source. you cannot continuously withdraw more than you deposit and maintain a balance. Something else is adding to the account. The answer lies inside the planet. Neptune is 4.6 billion years old, the same age as the rest of the solar system. When it formed, the collision and compression of enormous amounts of material generated tremendous heat. That heat has been radiating away ever since, but 4.6 billion years has not been enough time to fully exhaust it. Some of that original formation energy is still there, locked in the interior, slowly leaking outward. There is also a second mechanism at work. Neptune is not a static object. It is slowly contracting under its own gravity, compressing its interior, and that compression generates additional heat. Together, these two sources, residual formation heat and ongoing gravitational contraction, push Neptune's actual temperature above what solar heating alone would produce. Neptune is warmer than it should be because it is still, in a very slow sense, cooling down. This points toward a general rule that applies everywhere in the universe. Without an internal heat source, objects in space cool. They radiate energy outward. They receive less than they lose. The bank balance falls, and eventually an object without any ongoing source of incoming energy cools all the way toward the lowest temperature its surroundings allow. That lower limit is not zero. The universe itself is not empty of energy. Even the deepest, most remote regions of space have a background temperature, a faint thermal floor below which nothing can cool. What sets that floor, and where it came from, is the next question. And the answer reaches back to the very beginning of everything. The number has a name now. It is approximately 2.7 Kelvin, or about negative 454 degrees Fahrenheit. More precisely, negative 454.76 degrees Fahrenheit. That is the temperature of the coldest thing in the observable universe. Not a distant planet, not a cloud of gas between galaxies. The coldest thing in the universe is the universe itself. This is the cosmic microwave background radiation, the CMB. It is not a region of space. It is not a cold patch somewhere far away. It fills all of space, uniformly, in every direction at once. Right now, radiation at that temperature is passing through the walls of this room, through the ground beneath your feet, through you. It is everywhere, always, and it has been here for almost as long as the universe has existed. To understand where it came from, you have to go back, very far back. The universe is 13.8 billion years old. When it began, it was not dark and cold. It was the opposite. Extraordinarily hot. Extraordinarily dense. So hot that matter as we know it could not exist. There were no atoms, no molecules, no stars, no planets, no structure of any kind, just an intense, churning sea of particles, energy, and radiation, all packed so tightly together that light could not travel more than a short distance, before colliding with something and scattering. The universe was opaque, not dark. Opaque. The difference matters. Dark means no light. Opaque means light exists but cannot move through the medium. This early universe was more like the inside of a furnace than a void. Light was trapped. It bounced and scattered continuously, unable to travel freely in any direction. This continued for a very long time. For the first 380,000 years after the Big Bang, the universe stayed opaque. That sounds like a long time by human standards. On cosmic scales, it is the first breath of a 13.8 billion year story. Then something happened. As the universe expanded, it cooled. This is the direct consequence of expansion. Stretch any contained gas or plasma, and its temperature falls. The universe was doing this on a scale we can barely imagine, and as it did, the temperature dropped toward a critical threshold. Around 380,000 years after the Big Bang, the universe had cooled to approximately 6,000 degrees Fahrenheit. That number may sound familiar. It is roughly the surface temperature of the sun. At that point, something fundamental changed. Electrons, which had been too energetic to bind to atomic nuclei, finally slowed enough to be captured. Hydrogen atoms formed. Helium atoms formed. And because neutral atoms do not scatter light the way free electrons do, the universe became transparent almost at once. Not gradually, not partially. In cosmological terms, suddenly. The radiation that had been trapped, bouncing and scattering for 380,000 years, was released. It streamed out in all directions into a universe that was now clear enough to carry it. That moment, when matter and light separated for the first time, is called recombination. It is the moment the universe first became visible to itself. Here is what scientists found when they looked for that ancient light. It is still here. That radiation has been traveling for 13.8 billion years. As it traveled, the universe continued to expand around it. And this is where understanding what expansion actually does to light becomes important. Think about drawing two parallel lines across a rubber band. The lines represent the peaks of a light wave, the distance between them its wavelength. Now stretch the rubber band. The lines move apart. The wavelength gets longer. The energy of the wave drops. This is redshift. The expansion of the universe does this to every wavelength of light traveling through it. It stretches the light. At the moment of recombination, that released radiation had a temperature of roughly 6,000 degrees Fahrenheit. It was bright. It was hot. It peaked in wavelengths of visible and ultraviolet light. But over 13.8 billion years of expansion, that radiation has been stretched. Wavelengths that were once in the visible range have been pulled into the infrared, and then further, all the way down into the microwave range. The wavelengths are now much longer. The energy is much lower. The corresponding temperature has fallen from thousands of degrees to 2.7 Kelvin. But the radiation is still there. It fills space uniformly, not concentrated near galaxies, not clustered around anything. Everywhere, every cubic centimeter of space, in every direction, contains this ancient stretched light. The afterglow of the Big Bang, still present, still warm, still traveling, 13.8 billion years after the moment it was first set free. This is why empty space has a thermal flaw. Any object in space, left without an energy source, loses heat by radiating outward. You have seen that mechanism already. The object emits, receives less than it loses, and its temperature falls. But it does not fall to zero. It falls until it matches the temperature of its surroundings. And its surroundings are never truly empty. They are bathed in this radiation. The CMB sets the baseline. No object in the natural universe can cool below approximately 2.7 Kelvin, because the CMB is constantly arriving from all directions, delivering a floor of energy that cannot be removed. But the reality was different. Scientists have gone colder than this in laboratories on Earth. Using a technique called laser cooling, researchers can slow atoms almost to stillness by firing carefully tuned lasers at them. Combine this with magnetic traps, which hold the atoms in place, and you can remove energy from a sample until the atoms barely move at all. In laboratories today, scientists have cooled atoms to within roughly 1/1,000,000th of a degree above absolute zero. Not 1 degree, not 1,000th of a degree, 1/1,000,000th. At these temperatures, something unusual happens. A collection of atoms can enter a state where they stop behaving as individual particles and begin acting as a single, unified quantum object. This is called a Bose-Einstein condensate. Matter in a state that does not exist anywhere in the natural universe. A state colder than the interior of any star, colder than the space between galaxies, colder than the CMB itself. But this takes enormous effort, extraordinary equipment, extraordinary isolation. The moment the magnetic trap fails, the moment stray radiation or any outside energy leaks in, the sample warms. Nature does not produce these conditions. The coldest natural environment anywhere in the observable universe, the emptier space between galaxy clusters, is still warmer than these laboratory samples. The CMB is always there, arriving from all directions. keeping the natural floor at 2.7 Kelvin. The universe is not cold the way a freezer is cold. A freezer is cold because we removed heat from it and keep removing heat from it, actively, continuously. The universe is at 2.7 Kelvin because that is what remains of the heat it was born with. The CMB is not an absence of energy, it is the last remnant of the beginning. There is still more to the story of what happens when things get cold. Not in the largest structures of the universe, but in the smallest. There is one place nearby that is not quietly cooling toward that floor. One source that is not settling, not fading, not drifting toward equilibrium with the rest of the universe. The sun. And understanding the sun means understanding something that took physicists decades to work out. Because for a long time, the question of where the sun's heat comes from had no satisfying answer. Coal could not account for it. Gravity could not account for it. Every energy source anyone proposed burned out far too quickly to explain a star that had been shining for billions of years. The answer, when it finally came, required a different kind of physics entirely. The sun is powered by nuclear fusion. In the core, hydrogen nuclei are squeezed together under conditions so extreme that they overcome the electromagnetic repulsion that would normally keep them apart. When they collide with enough force, they fuse into helium, and when they do, a tiny fraction of their mass simply ceases to exist as matter. It becomes energy instead. This is what Einstein's equation describes. E equals mc squared. A small amount of mass, multiplied by the speed of light squared, produces an enormous amount of energy. The speed of light is already a staggering number. Squared, it becomes almost incomprehensibly large. So even a small mass disappearing produces a tremendous release. How much mass? Every second, the sun converts roughly 600 million tons of hydrogen into approximately 596 million tons of helium. The difference, about 4 million tons per second, it vanishes as energy. 4 million tons of matter every second converted entirely into radiation. That process has been running continuously for about 4.6 billion years, and it will continue for roughly 5 billion years more before the sun exhausts the hydrogen in its core. The core where this happens is not like any environment we have direct experience of. The density there is roughly 150 times greater than water. Think about that. Water itself already resists compression. At 150 times that density, the material in the sun's core is nothing like a gas in any ordinary sense, and the temperature there reaches approximately 27 million degrees Fahrenheit. The surface of the sun, by comparison, sits at around 10,000 degrees Fahrenheit. The surface is, by core standards, almost cool. But something was wrong. The energy released by fusion does not simply pour outward. A photon, a particle of light, born in that fusion reaction in the sun's core, does not travel to the surface in any direct way. The core is so dense that the photon barely moves before it is absorbed by surrounding matter and re-emitted in a completely random direction. Then absorbed again, then re-emitted again. In another random direction, over and over, thousands of billions of times. Think about a person trying to cross an enormous crowded room while blindfolded, and every few steps someone bumps them from a different direction. They move, but not forward. They wander. They drift in ways that look nothing like crossing a room. Over time they do cross it, but by a path so chaotic it bears no resemblance to a straight line. That is what happens to a photon inside the sun. The journey from the core to the surface, a distance of roughly 430,000 miles, takes approximately 170,000 years. Not 8 minutes, not 8 hours, not 8 years, 170,000 years of random, chaotic wandering through dense matter before the photon finally reaches the surface and escapes. And then, the 93 million miles to Earth takes about 8 minutes. The sun pours out energy at a rate of roughly 3.8 times 10 to the 26th watts. To put that another way, it is a 3 followed by 26 zeros worth of power, radiating outward in all directions every second. The total output is so large that human civilization could run for thousands of years on the energy the sun produces in a single second. And yet the space surrounding the sun stays cold. This is the core of the paradox. And it holds even knowing everything about fusion. The sun is blasting that enormous output into the surrounding volume continuously. But there is almost nothing in that surrounding volume to receive it. Vacuum does not warm. Radiation passes through it without depositing energy. The photons stream outward, crossing hundreds of millions of miles, and the space they cross remains as effectively temperatureless as it was before. The energy is real, the radiation is real, but nothing is there to become hot. The sun also pushes out a solar wind, a stream of charged particles, mostly protons and electrons, escaping from its outer atmosphere at roughly 300 miles per second. Individually, those particles carry kinetic energies equivalent to temperatures of millions of degrees. In that narrow sense, the solar wind is extraordinarily energetic. But this is where the distinction between energy and temperature matters. Near Earth's orbit, the solar wind contains only about 5 particles per cubic centimeter. 5. That is sparse beyond most intuitions. An object floating in the solar wind would receive almost no particle collisions per second. The heating effect from particle impact would be negligible. It is the photons, the radiation, that do the work. And the radiation only heats what it actually strikes. Other stars drive this point further. More massive stars than our sun burn hotter and faster, exhausting their fuel in millions of years rather than billions. Less massive stars burn cooler and slower, and some of the smallest will continue fusing hydrogen for hundreds of billions of years, far longer than the current age of the universe. Stellar lifetime scales with how aggressively the star is fusing. The sun sits near the middle of that range, steady and moderate, converting its mass into energy at a rate that keeps it stable. Stable because fusion output and radiative loss are in balance. The sun is not exploding outward or collapsing inward. It is holding a precise equilibrium between the pressure produced by fusion and the gravity pulling its mass inward. That balance has held for 4.6 billion years. Now consider what that equilibrium means for the space around it. The radiation streaming outward at full power goes almost entirely uncaptured, except in one place, where there is matter to receive it. Earth receives that radiation, but what Earth does with it depends critically on what Earth has around it. Strip away the atmosphere and the situation changes completely. The moon sits at almost the same distance from the sun as Earth. The radiation arriving at both surfaces is roughly comparable, but the moon's sunlit surface climbs to around 260 degrees Fahrenheit, and its shadowed surface drops to around negative 280 degrees Fahrenheit. A swing of more than 500 degrees between one side and the other, with nothing in between. The transition happens at the line where sunlight ends and shadow begins. Earth does not behave that way. Its day side does not bake to 260 degrees, and its night side does not freeze to negative 280 degrees. The reason is the atmosphere. Sunlight entering the atmosphere transfers energy to air molecules, which carry it, share it through collision and circulation, and redistribute it across the planet's surface. The atmosphere also absorbs infrared radiation emitted back up from the ground, and holds that energy in the air rather than letting it radiate directly to space. Winds carry heat from the warmer day side toward the cooler night side. Ocean currents do the same on slower timescales. The result is a surface temperature range that stays within a narrow band compared to the moon's extremes. Space has none of this. No air to absorb and hold. No medium to carry heat from one region to another by conduction or convection. No fluid to circulate. Only radiation streaming through a void, depositing energy only where matter exists to receive it, and otherwise passing through as if nothing were there. The sun is the brightest object in the sky by an enormous margin. The space immediately around it is colder than anything you would call warm. Both facts are true at the same time. The question is how they coexist, and the answer is the same answer that has appeared throughout this story. Energy is not temperature, and transmission is not transfer. The sun can pour its output into the universe without warming the universe, until something is there to catch it. That something, in our case, is a thin layer of gas wrapped around a rocky world. And what that layer does with the energy it catches turns out to be one of the most consequential facts about the place we live. That thin layer of gas is one answer to the problem of how something survives in space. But not everything gets the shelter of an atmosphere. Some things have to face it directly. Consider what an astronaut experiences on a spacewalk. On the sunlit side of the orbit, the suit's outer surface can exceed 250 degrees Fahrenheit. That is hotter than boiling water. On the shadowed side, the same suit can drop below negative 250 degrees Fahrenheit. Not after hours in shadow. Quickly. The swing happens because there is no air to buffer the change. Radiation arrives from the sun and heats the surface it strikes. When that surface rotates into shadow, it begins radiating its stored energy back out into space, and nothing stops it from cooling. The suit itself is a thermal engineering project as much as a protective shell. Without that engineering, the astronaut inside would not survive a single orbit. The Hubble Space Telescope experiences the same problem at larger scale. Hubble orbits roughly 340 miles above Earth's surface. Every orbit takes about 97 minutes. In that 97-minute period, Hubble passes through full sunlight and then into Earth's shadow and back again. In sunlight, its outer surfaces reach around 140 degrees Fahrenheit. In shadow, they drop to around negative 170 degrees Fahrenheit. That is a swing of more than 300 degrees, repeated roughly 15 times every day. Over 30 years of operation, that is hundreds of thousands of thermal cycles, pressing and releasing the telescope's structure. But the telescope keeps working. The reason is multi-layer insulation, a material that wraps critical components in thin, reflective sheets separated by vacuum gaps, and a network of small electric heaters that prevent sensitive instruments from dropping below their minimum operating temperatures. The insulation does not eliminate the temperature difference. It slows the rate of change enough that the telescope's components can survive it. The International Space Station manages the same challenge at larger scale still. One side of the station faces the sun, the other faces deep space. The difference between them is enormous, and the station cannot simply accept it. Instead, the ISS uses radiators, large panels that extend from the station's structure and radiate excess heat away into space, and heat exchangers, systems that move thermal energy from where it accumulates to where it can be safely released. The thermal control system aboard the ISS is not an afterthought. It is one of the station's fundamental survival systems, continuously working to balance an imbalance that never goes away. These are the realities close to the sun, where solar radiation still delivers meaningful energy. But follow the probes farther out, and the situation changes. Voyager 1 is now more than 14.5 billion miles from Earth. To put that distance in perspective, it is well beyond the orbit of Neptune, beyond the reach of the solar wind itself, out in the region of interstellar space where the sun's direct influence ends. At that distance, the solar radiation that reaches Voyager is so faint that solar panels would be useless. The sun, seen from where Voyager travels, would be just another star in the sky. So how does Voyager still function? The answer is nuclear decay. Voyager carries a radioisotope thermoelectric generator, an RTG, which is a device that converts the heat released by decaying radioactive material directly into electricity. The fuel is plutonium-238, a radioactive isotope that releases heat steadily as it decays. That heat runs a thermoelectric converter, which produces the small but steady electrical current that keeps Voyager's instruments and transmitters alive. But the plutonium does not decay forever at a constant rate. It is always declining. The power output has been falling since Voyager launched in 1977. Engineers have been managing that decline for decades, shutting down instruments one by one to conserve what remains, prioritizing the systems most essential for scientific return and communication. Around 2025, by the estimates of the engineers who have spent careers watching this slow countdown, the power will fall below the threshold needed to run any instrument at all. The transmitter will go silent. Voyager will stop sending data. And then something changes in the nature of the object itself. While it was transmitting, Voyager was a probe, a scientific instrument, a voice from the edge of the solar system. After the silence, it becomes something else. It becomes a relic. The RTG will continue decaying, releasing less and less heat as the centuries pass, and Voyager will begin radiating that heat away into space with nothing to replace it. Slowly, over an immense span of time, it will cool toward the only floor that space provides. That floor is the cosmic microwave background. The CMB temperature of roughly negative 454 degrees Fahrenheit. That is where everything in space eventually settles, absent any other energy source, not a metaphor. The trajectory is literal. A spacecraft that has traveled beyond the reach of the sun, with its fuel spent, will continue radiating its remaining heat outward until it reaches equilibrium with the faint warmth that fills the universe itself. Voyager is not alone in this fate. Pioneer 10, Pioneer 11, Voyager 2, New Horizons, all 5 are on trajectories that carry them away from the sun and out into interstellar space. Each travels at roughly 10 miles per second relative to the sun. Each will fall silent in turn as its power source exhausts. Each will cool. In tens of thousands of years, some of them may pass within a few light years of another star. In millions of years, the gravitational field of a distant star system might eventually capture one, drawing it in after an interstellar crossing that began with a rocket launch from a planet called Earth. Or none of that will happen, and they will drift outward forever, growing colder, crossing the long dark between stars with no destination and no power and no voice. Voyager 1 carries a golden record, a disk encoded with sounds and images from the civilization that built it, selected in the hope that something capable of finding it and playing it might one day exist. That record will outlast the spacecraft's warmth by an unimaginable margin. It will survive frozen, silent, drifting, long after the last of the decay heat has radiated away. This is the ultimate fate of every unpowered object in space. Radiate away what heat remains. Reach equilibrium with the background. Become cold. What that means for the stuff that powers itself, the objects that keep generating heat from within, is a different and older question. And it reaches back much further than any probe we have ever built. That question reaches back much further than Voyager. It reaches back to the beginning of everything. The cosmic microwave background sets a floor. We have established that. Everything in the natural universe cools toward it. Nothing natural falls below it. The CMB is the thermal baseline, the background hum of a universe that was once burning and has been cooling for 13.8 billion years. It sits at 2.7 Kelvin, and it fills all of space without exception. But here is where it gets strange. Some places in the universe are colder than the CMB itself. That should not be possible. If the CMB fills all of space, if it passes through everything everywhere at all times, then how can anything cool below it? The background radiation is always arriving. It is always depositing a small amount of energy into whatever it touches. Nothing should be able to shed heat faster than the CMB replenishes it. And yet, about 5,000 light years from Earth, there is a cloud of gas called the Boomerang Nebula. Its temperature is approximately 1 Kelvin, negative 458 degrees Fahrenheit. colder than the cosmic background, colder than the floor that everything else is cooling toward. The mechanism is adiabatic expansion. A dying star expelled this gas outward at roughly 100 miles per second. When a gas expands rapidly, it does work against its own internal pressure. That work draws down the internal energy of the gas. The molecules slow, the temperature drops, the gas is expanding so fast that it is losing heat faster than the CMB can put it back. For now, it is racing below the floor, not permanently. This cooling is temporary. As the expansion slows, the CMB will win. The nebula will warm back toward the background. But right now, in this moment, it is the coldest known natural place in the observable universe, colder than the ancient afterglow of the Big Bang. Now, move in a different direction, not toward the exotic and the brief, but toward the vast and the ongoing. Molecular clouds are among the coldest long-lived structures in the cosmos. These are dense regions of interstellar gas and dust, shielded from most incoming radiation by their own layers of dust grains. Inside, temperatures fall to around 10 Kelvin, roughly negative 441 degrees Fahrenheit. They are not as extreme as the Boomerang Nebula, but they persist. They are stable, and they are cold enough to harbor chemistry that would not survive anywhere warmer. More than 200 types of molecules have been detected in interstellar space, many of them inside these clouds. Complex organic molecules, carbon chains, the building blocks of things far more intricate. They survive because the temperature is low enough to keep them from breaking apart, and the dust shields them from the radiation that would destroy them. The dust grains themselves are doing the work. They absorb stray incoming radiation and re-emit it in the infrared, at wavelengths that escape the cloud easily. It is an efficient cooling pathway. The cloud sheds heat outward faster than it receives it from the sparse radiation that penetrates. The result is cold, deep, stable cold. The kind of cold that allows complexity to form. These clouds do not stay cold forever. When enough mass accumulates, gravity takes over. The cloud begins to collapse under its own weight. As it collapses, it compresses. Compression heats the gas. The temperature rises. Eventually at the core, conditions become extreme enough for nuclear fusion to ignite. A star forms. The cold nursery becomes a hot engine. That is the process that built the sun. It is the process that built every star in the sky. And that pivot brings the full range of the cosmos into view. The sun's core runs at roughly 27 million degrees Fahrenheit. We have covered what happens there. Hydrogen fuses into helium, and mass disappears into energy. But the sun's core is not the hottest place the universe produces, not remotely. When a massive star exhausts its fuel, the core collapses. The outer layers fall inward and then rebound outward in a supernova explosion. At the center of that collapse, temperatures briefly reach approximately 180 billion degrees Fahrenheit, 6,000 times hotter than the core of the sun. At these temperatures, atomic nuclei are torn apart and reassembled. The conditions are extreme enough to force together elements that nothing cooler could build. Heavy elements form here: gold, platinum, uranium, the raw material of chemistry that cannot be made anywhere else. The supernova then throws all of it outward into the surrounding space, where it mixes with molecular clouds, collapses into new star systems, and eventually ends up in planets, in oceans, in living things. Every atom of gold in any ring you have ever seen was forged in a supernova billions of years ago. Every iron atom in your blood was made in the death of a star, not as a metaphor, as a literal fact of nuclear physics and stellar evolution. But even 180 billion degrees is not the upper boundary of what the universe can produce. In August 2017, astronomers detected something extraordinary. Gravitational waves arrived at detectors on Earth. The ripples matched the signature of two neutron stars, spiraling into each other and merging. Within seconds, every major telescope on Earth and in orbit turned to the same region of sky. For the first time in history, A single cosmic event was observed simultaneously through gravitational waves and through light. Neutron stars are the collapsed remnants of massive stars that exploded as supernovae. They are made of matter compressed so far that the structure inside atoms has collapsed. A single teaspoon of neutron star material would weigh roughly 1 billion tons. Not slightly dense, 1 billion tons in a teaspoon. When two of these objects collide, the temperatures briefly reach into the trillions of degrees. The energy released in those seconds exceeds what the sun will produce across its entire 10 billion year lifetime. Every element heavier than iron, the full periodic table of heavy metals, is forged and scattered outward in those moments. The universe makes all of it in a flash, and yet the Big Bang itself was hotter still. At 1/10 trillionth of a second after the beginning, the temperature of the universe was approximately 10 trillion degrees Fahrenheit. Space itself was a sea of energy so dense that matter and radiation were indistinguishable. 1 second in, the universe had already cooled to roughly 10 billion degrees Fahrenheit. By 3 minutes, roughly 1 billion degrees, the conditions were mild enough for protons and neutrons to combine and form the first atomic nuclei. Hydrogen, helium, trace amounts of lithium. These are the elements that the first few minutes of cosmic history produced, and their proportions in the universe today match the predictions from that model precisely. Then, the cooling continued. At 380,000 years, the temperature fell to roughly 6,000 degrees Fahrenheit. Electrons joined nuclei, atoms formed, the universe became transparent, the trapped radiation escaped. We detect that escaped radiation today as the CMB, stretched by 13.8 billion years of cosmic expansion from visible and ultraviolet wavelengths all the way down to microwaves, now measured at 2.7 Kelvin. The universe has been cooling continuously since that first moment, from 10 trillion degrees to 2.7 Kelvin. An unbroken gradient stretching across all of time and all of space, and it has not stopped. The universe continues to cool. The CMB is getting colder. The expansion of space stretches its wavelengths further with every passing billion years, lowering its energy, dropping its temperature. The floor itself is falling. The coldest known natural place is a temporary cloud of gas cooling below a background that is itself declining. The hottest natural events occur in collisions that last seconds and then fade. Everything in between, every star, every planet, every living thing exists in the narrow corridor of temperatures between those extremes. A corridor that is, in cosmic terms, getting narrower. What determines where any particular object falls inside that corridor, and why some objects stay hot far longer than the physics of their surroundings would suggest, turns out to involve a mechanism much closer to home than any of these extremes. Some of those specific objects within that corridor sit at its most extreme edges, not in the largest structures of space, but in bodies dense enough to bend the fabric of reality itself. Neutron stars are what remain when a massive star exhausts its fuel and its core collapses in a fraction of a second. The collapse is violent. The rebound produces the supernova. And what is left behind is a remnant so compressed that roughly 1.4 times the mass of our entire sun is packed into a sphere about 12 miles across. That is smaller than many cities. A young neutron star radiates enormous heat from its surface. Surface temperatures near 1 million degrees Fahrenheit. Hot enough to pour out X-rays in every direction. But here is the crucial difference from a star. A neutron star has no fusion running inside it. There is no ongoing reaction generating new heat. It is simply a cooling object, like an ember pulled from a fire and left on a stone. The heat is real. The source is gone. So neutron stars cool. Not quickly by human standards, but relentlessly by any standard. Over millions and then billions of years, the surface temperature falls. Old neutron stars, those that formed billions of years ago and have been radiating ever since, have cooled to around 10,000 degrees Fahrenheit. Still extraordinary by any Earth measure. But compared to 1,000,000 degrees, that is already a profound collapse. Given enough time, they will cool further. Eventually, they will approach the temperature of the CMB itself. When that happens, they will radiate almost nothing. They will become what physicists call black dwarfs, invisible to telescopes, detectable only by gravity, objects that were once the engines of supernovae, reduced to cold, silent remnants drifting in the dark. But the cooling arc of neutron stars is not the strangest thermal story in this region of extremes. That distinction belongs to objects that seem, at first, to have no thermal story at all. Black holes are not usually described as cold. The image most people carry is one of violence, jets of energy, crushing gravity, radiation blazing at the edges of an accretion disk as in falling matter heats to extreme temperatures. But that is the environment around a black hole. The black hole itself is a different matter entirely. In 1974, the physicist Stephen Hawking calculated something that surprised nearly everyone working in theoretical physics at the time. Black holes, he showed, do emit radiation, not from the interior, which by definition cannot communicate with the outside universe, from the boundary, from the event horizon. The mechanism requires a brief detour into quantum physics. Empty space is not truly empty. At the quantum level, pairs of virtual particles are constantly flickering into existence and annihilating each other, too short-lived to affect anything in ordinary conditions. But at the edge of a black hole's event horizon, something unusual happens. A virtual pair can be separated by the boundary itself. One particle falls inward, the other escapes. The escaping particle carries away real energy. From the outside, the black hole appears to be emitting a faint glow of radiation. Think of it this way. The event horizon acts like a wall that catches one half of a pair that should have cancelled itself out, forcing the surviving half to become real and escape. This is Hawking radiation. Then the data shifted. The temperature associated with that radiation is not large. It is inversely proportional to the mass of the black hole. The more massive the black hole, the colder its Hawking temperature. For a black hole with roughly the mass of the Sun, the Hawking temperature works out to about 1/10,000,000th of a Kelvin. Not 1 degree, not 1,000th of a degree, 1/10,000,000th. That is far, far colder than the CMB's 2.7 Kelvin. For the supermassive black holes at the centers of galaxies, objects millions or billions of times more massive than the Sun, the Hawking temperature is effectively zero. In the present era, stellar mass and larger black holes are not just cold, they are absorbing more energy than they emit. The CMB bathes them constantly. More photons fall in than Hawking radiation carries out. They are growing, however slowly. Their evaporation timescale is not centuries or even billions of years. For a solar mass black hole, the time required to fully evaporate via Hawking radiation is approximately 10 to the power of 100 years. That is a 1 followed by 100 zeros. The current age of the universe is roughly 13 billion years, a number so vastly smaller that placing it next to 10 to the 100th is almost without meaning. For now, in the present universe, stellar mass and larger black holes are effectively the coldest large objects in the cosmos. There is one exception worth naming. Hypothetically, if very small black holes with masses perhaps comparable to a mountain formed in the first moments after the Big Bang, their Hawking temperatures would be billions of degrees. They would be blazing, rapidly evaporating objects, shrinking and brightening as they lost mass. No such primordial mini black holes have ever been observed. They may not exist, but the physics permits them. The exotic gives way now to the familiar, or what appears familiar. Mercury is the innermost planet. It orbits the Sun at roughly 36 million miles, closer than any other planet, receiving about 11 times the solar radiation that reaches Earth. The expectation then is obvious. Mercury should be the hottest planet, relentlessly baked by a sun that fills a far larger portion of its sky. And the day side confirms that expectation. Surface temperatures on the sunlit side reach about 800 degrees Fahrenheit, hot enough to melt lead, hot enough to melt zinc, a temperature that no unprotected machinery from Earth could survive. Then Mercury rotates, and because it has no atmosphere to hold heat, the night comes fast and absolute. Not fast in seconds, because Mercury turns slowly, each day lasting 58 Earth days, each night the same. But when the sunlight leaves a patch of ground, there is nothing to slow the heat loss. No air to retain warmth. No ocean to release stored energy through the long dark. The temperature plunges to approximately negative 290 degrees Fahrenheit. The swing from day to night exceeds 1,000 degrees. That is the largest temperature swing of any planet in the solar system. Not merely larger, the largest by a considerable margin. But the real surprise on Mercury is not the heat. Because Mercury's axis is nearly perpendicular to its orbit, the sun never rises above the horizon at the poles. Some craters near the poles sit in permanent shadow. Their floors never see direct sunlight. Not seasonally, not intermittently. Never. The floor temperature in those craters stays around negative 300 degrees Fahrenheit year-round, every year, for billions of years. Radar observations have detected water ice inside those permanently shadowed craters. Ice. On the closest planet to the sun. Not a trace amount. Measurable deposits of water ice, sitting frozen in shadow on a world where the sunlit ground is hot enough to melt metal. The shadowed crater acts as a cold trap. Any water that arrives, from comet impacts or volcanic outgassing over billions of years, migrates toward the poles and stays. The sun beats down a few miles away. The ice does not care. Comets carry a similar tension inside their own structure. They are remnants of the early solar system, bodies composed of water ice, frozen carbon dioxide, frozen methane, frozen ammonia, and dust, assembled in the cold outer reaches of the solar system billions of years ago. Far from the sun, they sit dormant at temperatures around negative 400 degrees Fahrenheit. Inert. Silent. Unchanged for billions of years. But when a comet falls toward the inner solar system, the symmetry breaks. The sunlit side warms as it approaches the sun. Near perihelion, the closest point of approach, the sunlit face reaches temperatures near freezing. The ice does not melt. It sublimates, passing directly from solid to gas without becoming liquid, because the pressure at the surface is too low to sustain liquid water. Gases and dust pour off the surface, blown back by solar wind and radiation pressure into the coma and tail that always points away from the sun. The shadowed side of the same comet, only feet or yards away from the active sunlit face, stays near negative 300 degrees Fahrenheit. Two faces of the same object, separated by a short distance and 1,000 degrees. That thermal stress does physical work. The ice expands as it warms, contracts as it cools, surfaces crack, material breaks away. Some comets fracture under the strain. In July 1994, Comet Shoemaker-Levy, 9 struck Jupiter in a sequence of impacts that observers on Earth watched across several days. But the fragmentation had happened earlier. Jupiter's tidal gravity, combined with the thermal cycling the comet had endured, had broken it into more than 20 separate pieces before the impacts began. The comet did not arrive whole. It arrived as a string of fragments, each hitting Jupiter individually, each producing an explosion visible through telescopes from Earth. Temperature does not only determine the state of matter, it determines the fate of structure. The same process that slowly cools a neutron star over billions of years, that holds ice in permanent shadow on a sunlit world, that cracks a comet along hidden fracture lines, is always working. Every surface, every interior, every object in the solar system is negotiating constantly between the heat arriving and the heat departing. And the outcomes of those negotiations turn out to be stranger and more consequential than the temperatures themselves would suggest. The same forces that cracked Shoemaker-Levy 9 apart were at work long before any comet reached Jupiter. They are at work on every object moving through space. And the machines we build and send out into those conditions have to survive them, or they fail. The challenge for spacecraft engineers is not simply cold and not simply heat. It is the swing. Near Earth's orbit, a spacecraft surface in full sunlight can exceed 300 degrees Fahrenheit. The same surface, rotated into shadow, can drop below a negative 250 degrees. That is a swing of more than 550 degrees, and it can happen over the course of a single orbit. The electronics inside need to stay within a much narrower range. Roughly negative 40 degrees Fahrenheit on the low end, roughly 140 degrees on the high end. That window is small. Keeping a machine inside it in an environment that swings more than 550 degrees is an engineering problem with no simple solution. But the reality was different. In a vacuum, the only tool available is the one mechanism that works without matter: radiation. You cannot pump heat away through the air, because there is no air. You cannot stir a coolant into motion through convection, because convection requires a fluid medium with mass and density. What you have is what a spacecraft surface does with light. It absorbs some. It reflects some. It emits some. The entire discipline of spacecraft thermal engineering comes down to controlling those three quantities. Surfaces that are white and highly reflective push visible sunlight away while still radiating their own infrared heat outward. Engineers call these second surface mirrors, and they appear on spacecraft that need to stay cool. Surfaces that are black absorb visible light efficiently, but also radiate infrared efficiently, which makes them useful when you want a component to shed its own heat quickly. Choose the wrong surface coating on the wrong component, and the machine runs too hot or too cold. The choice of what color a panel is, and what material coats it, is not aesthetic. It is thermal management. Multi-layer insulation takes this further. The shiny gold and silver blankets wrapped around satellites and probes are not decorative. Each blanket is a stack of thin layers, typically aluminized mylar or a material called capton, separated by tiny gaps that provide almost no conduction path. In a vacuum, there is nothing to conduct through anyway. The blankets exist entirely to reflect infrared radiation back and forth between layers, slowing the rate at which heat escapes or enters. Each layer reflects rather than absorbs. Stack enough of them, and you can dramatically slow the rate at which a spacecraft's temperature changes, buying time against the extremes of sunlight and shadow. Active control goes further still. On the International Space Station, passive insulation is not enough. 6 human beings produce significant heat simply by existing. At rest, each person generates roughly 340 British thermal units per hour, a unit of heat energy roughly equivalent to what a small candle produces. 6 people, moving and working and sleeping, add up to a continuous heat load that the station cannot radiate away on its own. The station uses ammonia flowing through external cooling loops. The ammonia picks up heat from the station's interior and carries it out to large external radiators. Those radiators are oriented edge-on to the sun, which minimizes the solar radiation they absorb, while maximizing the infrared they emit outward into space. The station's interior stays near 70 degrees Fahrenheit. Without that system running continuously, it would not. Heat pipes offer a passive alternative for smaller systems. A heat pipe is a sealed tube containing a working fluid. At the hot end of the tube, the fluid evaporates. It travels as vapor to the cold end, where it condenses and releases its heat. Then it flows back as liquid to begin again. No pumps, no moving parts. The thermodynamics of the fluid itself drives the circulation. Heat pipes appear throughout spacecraft design wherever a quiet, reliable, unpowered path is needed to move heat from one place to another. Then, there is the James Webb Space Telescope. And this is where passive thermal engineering reaches something that should not be possible. Webb observes the universe in infrared. Infrared is heat radiation. If the telescope itself is warm, its own thermal glow drowns out the faint signals arriving from distant galaxies. To do its job, Webb needs to be extraordinarily cold, not merely cool, not kept below room temperature. The instruments must operate at around negative 390 degrees Fahrenheit. That is within about 50 degrees of absolute zero. The solution was a sun shield roughly the size of a tennis court. 5 layers of kapton, each coated to reflect sunlight, stacked with gaps between them. The sun-facing side of the shield sits at around 200 degrees Fahrenheit. The telescope-facing side sits at around negative 390 degrees Fahrenheit. The shield drops the temperature by roughly 600 degrees across its 5 layers. What it does not use is any refrigeration at all. No coolant loops, no compressors, no active cryogenic system. Webb cools to negative 390 degrees passively, using only the geometry of the shield and the natural cold of deep space. The telescope radiates its own heat outward, and nothing conducts it back in, because there is nothing to conduct through. On Earth, cooling an object to negative 390 degrees requires active refrigeration running continuously, because the atmosphere would conduct heat back into the cold object the moment the cooling stopped. In the vacuum of deep space, that path does not exist. The atmosphere that makes active cooling necessary on Earth is also the thing that makes passive cooling impossible here. Remove the atmosphere, and the same physics that creates lethal temperature swings also creates the conditions for one of the most precise passive cooling systems ever built. The bigger a spacecraft's distance from the sun, the less sunlight it receives. The relationship is precise. At Earth distance, roughly 1,360 watts of solar energy arrive on every square meter of surface facing the sun. At Mars, about 590 watts. At Jupiter, about 50 watts. At Neptune, roughly 1.5 watts per square meter, less than 1% of what reaches Earth. Beyond a certain distance, solar panels cannot generate enough power to run a spacecraft. The sun simply becomes too faint. That is where nuclear power takes over. Radioisotope. Thermoelectric generators, called RTGs, use the natural radioactive decay of plutonium-238, which has a half-life of roughly 88 years. Plutonium-238 decays slowly and steadily, releasing heat over decades. Thermoelectric converters turn some of that heat into electricity. The rest of the heat is not wasted. On Mars, where nights can drop to negative 100 degrees Fahrenheit or colder, the waste heat from an RTG flows into the rover's electronics bay, keeping instruments at operating temperature through the night without a dedicated heater drawing additional power. The Voyager probes, Cassini at Saturn, New Horizons past Pluto, and the Mars rovers, Curiosity and Perseverance, all carry RTGs. Each one is sustained not by sunlight, but by the slow transformation of matter. Atmospheric re-entry is the other extreme. Everything described so far involves surviving the cold and the heat of space. Re-entry is the problem of surviving a violent collision between a spacecraft and air. The Apollo command module re-entered Earth's atmosphere at roughly 25,000 miles per hour. At that speed, the air in front of the capsule cannot get out of the way fast enough. It compresses. Compression heats it. The compressed air in front of Apollo reached temperatures near 5,000 degrees Fahrenheit, hot enough to strip electrons from the gas molecules and create plasma, which is ionized gas. That plasma formed a sheath around the capsule that blocked radio communication. For several minutes during every Apollo return, Mission Control heard nothing. Not interference, not static. Silence. The plasma itself blocked the signal. Engineers had predicted this. They called it the blackout period. Knowing it would happen did not make the silence any less complete. The heat shield on Apollo was made from a material called avcoat, a resin filled with silica fibers. Avcoat does not simply insulate, it ablates. It vaporizes and erodes deliberately, carrying heat away in the material itself as it burns off. The shield gets consumed, so the capsule survives. Mars entry is different in a specific and important way. The Martian atmosphere is far thinner than Earth's. A spacecraft enters slower than Apollo did, around 13,000 miles per hour. But the thinner air means less compression heating, and more radiative heating. The plasma glows hot and radiates that heat directly onto the shield, rather than transferring it through collisions. The heat shield material used for Mars entry is called pica, phenolic impregnated carbon ablator, which handles higher radiative flux than avcoat. When the Mars Science Laboratory, carrying the Curiosity rover, entered the Martian atmosphere, the peak heating flux on the shield reached roughly 60 watts per square centimeter. The shield surface temperature climbed to around 4,000 degrees Fahrenheit. Inside, the rover never came close to those temperatures. The shield absorbed the energy and carried it away in the ablating material. The engineering between the plasma and the payload was measured in inches of engineered material. Every one of these solutions, from the reflective coatings on a satellite to the Kapton layers behind Webb's sun shield to the ablating heat shield on a Mars entry vehicle, is a direct answer to the same underlying physics. In a vacuum, radiation is the only path. The only question is what you do with it. And the further out you go, the more the answers change. Which brings us to the question these conditions have always implied. Not how we protect life we brought, but where temperature already permits life to exist on its own. The answer starts with water. Life as we know it requires liquid water, and liquid water has a narrow window. At Earth's atmospheric pressure, water freezes at 32 degrees Fahrenheit and boils at 212 degrees. Below that range, it locks into ice. Above it, it escapes as vapor. The window where it flows as a liquid, where it can dissolve nutrients and carry chemistry from place to place, spans exactly 180 degrees. On the scale of the universe's temperature range, from 10 trillion degrees at the Big Bang down to 2.7 Kelvin today, that 180-degree window is almost nothing. Every star has a region around it where a planet at the right distance could hold liquid water on its surface. Not too hot, not too cold, just right. For our Sun, that zone runs roughly from 93 million miles outward to about 150 million miles. Earth sits near the inner edge. Mars sits near the outer edge. Venus sits well inside at 67 million miles from the Sun. Venus is worth pausing on. Venus receives more sunlight than Earth. Its thick atmosphere, composed of roughly 96% carbon dioxide, traps that energy and refuses to release it. The result is a runaway greenhouse effect. The surface pressure on Venus is about 90 times Earth's atmospheric pressure, roughly equivalent to being half a mile underwater. And the surface temperature hovers around 900 degrees Fahrenheit. That is hotter than Mercury, despite being nearly twice as far from the Sun. Any water that once existed on Venus was long ago driven off into space or locked permanently into rock. Liquid water is not possible there, not in any form, not anywhere on the surface. Mars tells the opposite story, and a stranger one. Mars sits at the outer edge of the habitable zone. Its average surface temperature is around -80 degrees Fahrenheit. Its atmosphere is roughly 1% as dense as Earth's, too thin to hold heat effectively, too thin to keep surface water liquid. By every current measure, Mars is frozen and dry, but the picture did not hold. Mars is covered in ancient river valleys, carved channels, features that only liquid water moving in the large volumes over long periods of time can produce. Mars was not always frozen. Something changed. What changed was the magnetic field. Mars lost its global magnetic field billions of years ago, and without it there was nothing to deflect the solar wind. the constant stream of charged particles flowing outward from the sun. The solar wind stripped the Martian atmosphere away, particle by particle, over billions of years. As the atmosphere thinned, the greenhouse effect weakened. The planet cooled, water froze or escaped. The Mars that exists today is the end state of that long, irreversible process. Most of the water that once flowed on Mars is now locked in polar ice caps and subsurface permafrost. But deep underground, where pressure and residual geothermal heat are high enough, liquid water may still exist. If it does, that is exactly where life might persist, in cold, dark pockets far beneath the frozen surface, insulated from the thin atmosphere above. That possibility is one of the central questions driving Mars exploration today. Now comes the deeper surprise. The traditional habitable zone defines where surface liquid water is possible, but it is not the only place liquid water exists. Europa, one of Jupiter's moons, has a surface temperature of around -260 degrees Fahrenheit. Its surface is a sheet of ice roughly 10 to 15 miles thick. By every surface measurement, it is one of the coldest, most hostile environments in the solar system. Beneath that ice crust, there is an ocean, not a small one, a global ocean, possibly around 60 miles deep, containing more liquid water than all of Earth's oceans combined. It is not kept liquid by sunlight. It is kept liquid by tidal heating. Jupiter's enormous gravity flexes Europa's interior as the moon orbits, generating friction deep inside the rock, and that friction produces heat. That heat keeps the ocean liquid. The habitable zone, defined by the sun's reach, stops well short of Jupiter's orbit. Europa's ocean exists because of a different heat source entirely. Saturn's moon, Enceladus, tells a similar story with even more direct evidence. Geysers erupt from its south polar region, plumes of material blasting up through cracks in the ice and into space. The Cassini spacecraft, which orbited Saturn from 2004 until 2017, flew directly through those plumes and sampled what they contained. The results were remarkable. Water vapor, ice particles, and organic molecules, the chemical building blocks associated with life. Enceladus has a subsurface ocean tidally heated by Saturn's gravity, actively venting material into space. Cassini essentially handed us a sample from an ocean we have never directly reached. Titan, Saturn's largest moon, offers something stranger still. Titan's surface temperature is around -290 degrees Fahrenheit. Far too cold for liquid water, but Titan has weather, it has rainfall, it has rivers, lakes, and seas spread across its surface, not water, liquid methane and ethane. Titan has a complete hydrological cycle, the same kind of cycle Earth runs with water, but with methane as the working fluid. Methane evaporates from the surface, rises, forms clouds, rains back down, and collects in lakes and rivers that drain into seas. It is a strange parallel to Earth, every step recognizable, every substance completely different. Whether any form of life could exist in liquid methane is unknown. It would require biochemistry radically different from anything we know. Different solvents, different reactions, different structures at every level. Not impossible, just completely outside our current experience. Beyond our solar system, thousands of exoplanets have been discovered, many of them orbiting within what astronomers calculate as their star's habitable zone. The nearest known exoplanet, Proxima Centauri b, orbits its red dwarf star at roughly 4.6 million miles, far closer than Earth is to the Sun. But because Proxima Centauri is much cooler and dimmer than our Sun, the planet receives roughly similar radiation to what Earth receives. That should sound promising, but red dwarfs are not calm stars. Proxima Centauri produces flares that briefly increase its brightness by more than 10 times, releasing intense ultraviolet radiation and X-rays. Without a strong magnetic field and a thick atmosphere, Proxima b's surface could be stripped and sterilized by those flares repeatedly over millions of years. We cannot yet measure whether Proxima b has a magnetic field. We cannot yet measure the density or composition of its atmosphere. We are looking at it from across 4.2 light-years of space, drawing careful inferences from faint signals. Telescopes, like the James Webb Space Telescope, can analyze the atmospheres of some exoplanets by measuring how light filters through them as the planet passes in front of its star. If astronomers detect oxygen, methane, and water vapor together in an exoplanet's atmosphere, that would be strong evidence of life, not conclusive. There are non-biological processes that can produce each of those signatures individually, but together, in the right proportions, they would be the most compelling signal we have ever found. There is one more piece to the picture. We have been assuming that life requires the relatively comfortable conditions of Earth's surface, but life on Earth does not confine itself to comfortable conditions. Organisms called thermophiles live in the hot springs of Yellowstone at temperatures around 200 degrees Fahrenheit, thriving in water that wouldn't scald a human being. Organisms called psychrophiles, cold-loving microbes, live in Antarctic ice and deep ocean water at temperatures around 28 degrees Fahrenheit, surviving through antifreeze proteins and slowed metabolisms that allow chemistry to continue where most biology would stop. Bacteria have been recovered from permafrost that had been frozen for hundreds of thousands of years. When thawed and given nutrients, they became active again. The frozen state had not killed them. It had only paused them. If Earth life can survive those extremes, then the boundary of where life could exist elsewhere expands considerably. The subsurface of Mars could harbor cold-adapted microbes. Europa's ocean, if it contains hydrothermal vents, similar to the ones on Earth's ocean floors where life flourishes without sunlight, could support heat-adapted organisms. Titan's methane seas might host something we would barely recognize as alive. The thermal framework is not just a story about temperature, it is a map of possibility. And the possibility space, it turns out, is much larger than anyone expected. That possibility space stretches outward from icy moons and frozen deserts, but it also reaches inward, back to the homeworld itself. And the same thermal physics that governs life's limits on Europa or Titan also governs why Earth is warm enough to host life at all. The sun radiates across an enormous spectrum. Gamma rays, X-rays, ultraviolet, visible light, infrared, radio waves, each carries different energy. But the sun peaks in visible light because its surface sits at roughly 10,000 degrees Fahrenheit, and a surface at that temperature radiates most intensely in wavelengths the human eye can detect. That is not a coincidence. Human eyes evolved to match the peak output of the star they formed under. At the top of Earth's atmosphere, the sun delivers about 1,360 watts per square meter. That is the solar constant. Of that energy, roughly 6% arrives as ultraviolet, 44% as visible light, and 50% as infrared. The ozone layer absorbs most of the ultraviolet before it reaches the surface. Water vapor and carbon dioxide in the atmosphere absorb some of the infrared. What gets through to the ground is mostly visible light and near infrared. That energy warms the surface. The surface, in turn, re-radiates the energy outward as infrared, as heat. And here is where the greenhouse mechanism enters. The atmosphere does not stop sunlight from coming in, but it does slow infrared from going back out. Greenhouse gases, carbon dioxide, methane, water vapor absorb outgoing infrared radiation and re-emit it in all directions. Some of that radiation heads outward to space, but some heads back down toward the surface. The planet traps a portion of its own heat. Without that effect, Earth's average surface temperature would sit near 0 degrees Fahrenheit. The oceans would be largely frozen. Life as it exists would be impossible. With the greenhouse gases currently in the atmosphere, Earth's average surface temperature is roughly 59 degrees Fahrenheit. That 59-degree difference is not incidental. It is the reason everything alive on this planet exists. Then the pattern broke. The same mechanism that makes Earth habitable, when amplified, makes a planet uninhabitable. Venus has an atmosphere that is 96% carbon dioxide. Its surface pressure is roughly 90 times that of Earth's, the equivalent of being nearly a mile underwater. And its surface temperature is approximately 900 degrees Fahrenheit. Not warm, not uncomfortably hot, hot enough to melt lead. Venus is hotter than Mercury despite being almost twice as far from the Sun. The greenhouse effect did not make Venus hospitable. It ran away. Earth sits in a narrow range, enough greenhouse gas to lift the surface temperature into the liquid water window, not so much that the planet becomes an oven. The balance is precise, and it is not permanent. Albedo adds another layer of complexity. Albedo is a measure of reflectivity, the fraction of incoming light a surface bounces back without absorbing. Fresh snow reflects roughly 80 to 90% of the sunlight that strikes it. Ice reflects 50 to 70%. Forests absorb most of what falls on them, reflecting only 10 to 20%. Oceans, darker still, reflect only 6 to 10%. When ice melts and exposes the darker land or water beneath it, the surface absorbs more energy than the ice did. More absorption means more warming. More warming means more melting. The process feeds itself. This is the ice albedo feedback loop, and it is the primary reason polar regions are warming faster than the rest of the planet. The feedback is not a future concern, it is operating now. The same albedo principles that govern polar warming also govern spacecraft design. White surfaces reflect incoming energy and stay cool. Black surfaces absorb it and warm. Gold-colored foil reflects infrared while allowing some visible absorption. Every coating choice on a spacecraft is a thermal decision. The physics does not change based on scale. Now pull back from Earth entirely. Think about what happens to a world that has no star at all. Early in the formation of planetary systems, gravitational encounters between young planets can slingshot bodies outward at escape velocity. These ejected worlds drift free of any star. No sunlight, no tidal heating, nothing but the faint, uniform warmth of the cosmic microwave background at 2.7 Kelvin. Without an internal heat source, these rogue planets cool toward that floor and stop. They become dark, frozen worlds drifting through interstellar space, impossible to see directly. We can detect them only through gravitational microlensing, the brief brightening of a background star when a rogue planet's gravity bends the light passing near it, or through faint residual infrared emissions from whatever warmth remains inside. The number of rogue planets in our galaxy is not known precisely, but estimates suggest there may be billions of them, possibly more rogue planets than stars. Consider what that means for Earth. If the sun were simply removed, the surface would begin to freeze within days. Within weeks, the oceans would start to freeze from the top down. Within months, the atmosphere itself, nitrogen and oxygen and the rest, would condense out and fall to the ground as snow. Earth would cool toward the cosmic microwave background. It would become another dark, frozen world, drifting in the dark, indistinguishable from the billions of others already out there. Our situation is not the default, it is the exception. A stable star, the right orbital distance, a substantial atmosphere, a magnetic field to shield against solar wind, active plate tectonics to recycle carbon, and regulate the long-term climate. Remove any of those factors and the thermal balance shifts. Earth's habitability is a configuration, not a guarantee. Future humans living beyond Earth will have to engineer that balance from scratch. On the Moon, the thermal problem is severe. The lunar day lasts 29.5 Earth days, 14 days of continuous sunlight, followed by 14 days of continuous darkness. Equatorial temperatures swing from roughly 250 degrees Fahrenheit in full sunlight to nearly negative 280 degrees Fahrenheit in the long lunar night. Nothing in a surface habitat survives that swing passively. But lava tubes, ancient volcanic tunnels beneath the surface, maintain a stable temperature near -20 degrees Fahrenheit year-round. They also block radiation and micrometeorite impacts. Underground habitats are not a romantic idea. They are a thermal necessity. Mars presents a different version of the same problem. Daily temperature swings on Mars exceed 100 degrees Fahrenheit, driven by the thin atmosphere's inability to hold heat through the night. Future Martian habitats will require multi-layer insulated walls, nuclear or solar heating systems, and possibly regolith packed around the structure, using Mars's own soil as insulation. In the outer solar system, past Jupiter, solar panels produce too little power to be the primary energy source. Nuclear power becomes essential, and the waste heat from a nuclear reactor is no longer a problem to be managed. It is a resource, but here is the inversion. A large enough Mars colony running at industrial scale might generate so much waste heat from manufacturing and energy production that it needs dedicated radiators to shed the excess. The same physics that forces a small outpost to fight for warmth would force a large colony to fight against it. The thermal problem does not disappear. It reverses. Think about the largest hypothetical structures ever considered. A Dyson sphere, a shell built around a star to capture most of its energy output, would glow in infrared from its own waste heat. The second law of thermodynamics does not allow perfect efficiency. Energy used is energy degraded. The structure would radiate its inefficiency into space as infrared light. An O'Neill cylinder, a rotating habitat in space, would balance sunlight collected on one end against radiator output on the other. Even in a civilization spanning star systems, the thermal balance still holds. Over cosmic time, all of it runs down. The universe is expanding. As it expands, the cosmic microwave background continues to cool. In 1 trillion years, the background temperature will be far lower than 2.7 Kelvin. In roughly 10 to the 14th years, that is a 1 followed by 14 zeros, stars will have exhausted their fuel. The galaxies will disperse. Black holes will remain, slowly evaporating via Hawking radiation over timescales approaching 10 to the 100th power. A 1 followed by 100 zeros. When even the black holes are gone, only a thin, diffuse soup of photons and particles will remain. No temperature differences to drive heat flow. No more processes that use energy, maximum entropy. This is what physicists call the heat death of the universe. It is not a violent end. It is an asymptotic quiet, everything gradually approaching the same temperature, which is to say, no temperature at all in any meaningful sense. The current universe is 13.8 billion years old. That is roughly 10 to the 10th power years. The heat death is 10 to the 100th power years away. We exist in the first instant of cosmic time. The early warm phase. Everything bright around us is a temporary condition. And yet, in this early warm phase, here is what is happening when sunlight falls on your skin. A photon began its journey in the sun's core, where hydrogen fuses into helium and mass converts to energy. That photon spent approximately 170,000 years bouncing through the dense interior of the sun, absorbed and re-emitted countless times in random directions, slowly working outward. Then it reached the surface and traveled 93 million miles of vacuum in 8 minutes. When it reached your skin, it was absorbed. Its energy became thermal motion in the molecules of your body. You felt it as warmth. Space was cold along the entire path. Not because the photon chilled it, because space is empty, and empty space has no matter to absorb energy and register a temperature. The sun is hot because it is dense matter undergoing fusion. Space is cold because it is not matter at all. Radiation is the thread between them. And that thread is why astronomy is possible. Space is transparent to most forms of radiation. Light from a star 100,000 light years away crosses that distance almost entirely unimpeded. We receive it, analyze it, and learn what the star is made of, how fast it moves, how hot it burns. The physics of heat transfer, The same principles that govern a warm surface losing heat to the night sky connect every object in the universe to every other object, across any distance. One question, why space is cold while the sun is hot, carries the entire structure of modern science inside it. It leads to nuclear fusion and stellar lifetimes. It leads to climate physics and planetary habitability. It leads to spacecraft engineering and the survival of future colonies. It leads to the long fate of the cosmos and the heat death waiting at the end of time. And it leads back to a single human moment, standing in the light, feeling the warmth of a nuclear furnace 93 million miles away, registered only because matter exists to receive it. The physics does not distinguish between scales. The smallest sensation and the largest structure obey the same rules and always will, for as long as there is energy left to flow